Okay, all the recordings are going. All right, so you've just turned in homework assignment number 1, and I did get a couple of questions about that as students were working through the assignment. As always, I'm eager to help you learn, and so if you get hung up on something, feel free to give me a call on Teams. And what I like about that is that then it can be an interactive discussion where if you have a follow-up question, we can just talk through it together, or you can maybe share your screen and show me what you've solved so far. Email is okay also, but it's just email is an impoverished form of communication because it's one-directional communication, and so it's much better if two people can communicate together in real time. So I like Teams, but email's okay too. Your next assignment is posted now on Blackboard. It's available. Homework 2 is due on Wednesday the 3rd. Like today's assignment, needs to be submitted before 1 o'clock. Today we're going to be talking about some improved ways of calculating the friction factor F that can give you more precision and are suitable for automation in a way that the Moody diagram is not. And then we'll apply some of those ideas in looking at a formula and method for designing the required diameter of a pipe. So this is in chapter 8 of the textbook. Any questions before we get started?
Yeah, Dr. Wade.
Yes?
Does delta Z, when you're dealing with the energy equations that we use for the homework, does delta Z equal Z2 minus Z1? And does delta P equal P1 minus P2, or do they both equal the 1s minus the 2s?
It may depend on the circumstances. Like if it says to find the pressure change in a pipe, then you'd presume that the pressure is decreasing. And so then that would be the lower pressure minus the higher pressure. And so it would be P2 minus P1 would tell you the pressure decrease. But if it already says, like in the problem statement, how much does the pressure decrease, then you don't have to put the negative sign into your answer. And so I think rather than saying it's always going to be one way or the other, I'm going to hedge my bets and just say it depends on the circumstances or on the problem description. If there's a specific case where you were wondering about that, it may be useful for us to look at that specific case rather than try and give you a general rule that may not apply in other cases. Okay, so you remember the Moody diagram, and it's a simple way of determining the friction factor over here on the left axis if you know the flow conditions, meaning if you know the Reynolds number and if you know the relative roughness, then you can find the friction factor intercept. But the problem with this is a lot of times we're going to have to calculate iteratively using the Darcy-Weisbach equation because the flow rate will depend on the friction factor, and the friction factor depends on the flow rate. And so there's kind of like a chicken and the egg thing that goes on where you can't know the Reynolds number until you know the flow velocity, but the flow velocity depends on the friction factor. And so the Moody diagram will be relatively less convenient for us in those implicit situations where we're having to iterate in order to find the friction factor and the flow velocity. And so a more robust way of calculating the friction factor, and in fact the formula that this diagram is based on, this diagram was generated by someone who was applying the Colebrook equation. This is valid anytime the Reynolds number is above the threshold for laminar flow. If it's below laminar, we've already talked about how you can find the F value is 64 divided by the Reynolds number. So otherwise, if it's outside of that laminar range, you can use the Colebrook equation. And so what you see in this Colebrook equation, first of all, is that the F value, which is what you're trying to solve for, is on the left side of the equation and on the right side of the equation. And so that means it's an implicit equation, and you could try and rearrange things algebraically all day long. You're not going to be able to isolate that variable. It's on both sides of the equation. It's buried inside a logarithm in the denominator under a square root. And so these F values are on both sides of the equation, which means to solve for F, you have to take a trial and error approach. So that's one first thing that I wanted to point out about this Colebrook equation, is that it's implicit. The other aspect of the F value that's interesting is that it depends on two terms inside of this logarithm. The first term is the relative roughness component. And so here I'm circling on the left side inside the logarithm. K sub s divided by 3.7d says that the F value in part depends on the ratio of the pipe material's equivalent sand roughness. That's what K is. K is how rough or how smooth is the pipe. That relative to the diameter of the pipe. So that's part of what determines F. And the other part of what determines F is the flow conditions. So the Reynolds number is in the second of those two terms inside the logarithm. So F value partly depends on the roughness of the pipe, and it partly depends on how quickly the flow is going through the channel. Both of those terms play a role. And so this equation is best solved if you have an equation solving calculator, or solving it on the computer is also possible with Excel. We'll take a crack at that today. Remember, we have a couple of different references that will tell us the equivalent sand grain roughness. This source is, I think, from your fluid mechanics textbooks, which the fluid mechanic textbook that you had called Equivalent Sand Roughness K sub s, our book for 331 calls it epsilon, and there's a similar table with these same numbers. But the idea here is that you have to know the relative roughness and also the flow conditions to determine accurately what is F. So just as an example of how to solve the Colebrook equation, let's try doing this with Microsoft Excel. Let's say that we have a galvanized iron pipe, and so galvanized iron, we could go to the table and find the relative roughness for it, the 0.15, and then divide that by the diameter. And the flow velocity is going to be determined by the flow rate of 200 liters per second and then the diameter of the pipe. So we'll be able to calculate the flow velocity from that. Let's use Microsoft Excel to determine what is the applicable F value here when we have the Reynolds number that we're going to calculate using just the typical kinematic viscosity of water of 1 times 10 to the minus 6th meters squared per second. Okay, so I'm going to copy that formula and then just start a fresh instance of Excel, and you can follow along. Hopefully, if you have access to a second screen, that'll be pretty useful this semester, because the second screen will allow you to have my demonstration going on one screen while you're working on the other. And most people may not think they have a second screen, but if you have a flat screen TV, most likely it has like an HDMI output. And so what you could do is you could plug your TV into the laptop and then extend. And so the TV has maybe my lecture, and then you're working on the laptop to follow along. All right, so here's the Colebrook equation, and then the flow conditions that we have that are described in this example. The diameter of the pipe is 136 millimeters. We know the K sub s. So let me put some of this information in here. The K sub s in terms of millimeters is 0.15. Let me make it a little bit bigger so it's not so small on your end. All right. And then we want to have the diameter of the pipe is 136 millimeters, and the Reynolds number that we're going to calculate, it is the, we may not have yet the flow velocity calculated. Okay, so 200 liters per second. So let me start with this. Q in terms of liters per second is 200. So then Q in terms of cubic meters per second is going to be that divided by 1,000. So that gives me 0.2 cubic meters per second. From the diameter of the pipe, I can get the cross-sectional area of the pipe. So it's pi times d, pi d, and I'm going to convert the diameters from millimeters to meters. So pi d squared, diameter squared, divided by 4. So that is the diameter of the pipe turned into the cross-sectional area. I hope I've got that right. Yes, that's correct. All right, so then the velocity in terms of meters per second is going to be Q divided by A. So flow rate divided by area gives me 13.77 meters per second. So the water's really moving fast through this conduit. All right, now it'll be easier for me to calculate the Reynolds number. Let me just put the kinematic viscosity in terms of meters squared per second, just so that we have that available to adjust as necessary. 1e minus 6. Okay, so that's 10 to the minus 6th. And now, finally, Reynolds number. So it's the velocity times the diameter. Now, my diameter is as millimeters, so I need to diameter divided by 1,000 to get that into meters. Okay, so now divided by kinematic viscosity. So the Reynolds number, 1.87 times 10 to the 6th. All right, so I'm going to be putting all of this into the formula, and I want to calculate the left-hand side and the right-hand side with a variety of guesses. And so I'm going to have a guess of F. And then I'm going to have the left-hand side of the equation, the right-hand side of the equation, and then the difference. Okay, so if my guess of F, the lowest value of F that you would generally see could be starting at 0.008. And what I'll do is I'll say, what about 0.009 as well? And then I'm just going to do it over the entire spectrum of typical F values. Maybe an upper end F value could be 0.038. All right. So one more. Okay, so I've got all those different F values, and I'm going to automate calculating the left-hand side of the equation. So on the left-hand side, I just have equals 1 divided by square root of F. So this is the left-hand side of the equation if F is that. Now I'll also calculate the right-hand side of the equation using this guess of the F value. Okay, so equals -2 times the logarithm of K sub S, and it's okay if it's in millimeters if I'm going to be then dividing by units of millimeters as well. So K sub S, and I'm going to anchor that reference so that when I drag the formula down, it always looks in the right spot for K sub S. Okay, so that's K sub S divided by 3.7 divided by D. Now another way to write that is divided by 3.7 times D, but I'll often do just the double divided by because it ends up being fewer keystrokes, I think. But for now, I'll leave it like this since it's already there. Okay, so K sub S divided by 3.7 times D, and I'll anchor the reference there. So now that's this term that is done, plus 2.51 divided by the Reynolds number. So I'll anchor the reference to here, times the square root of F. Pretty hairy, right? You're going to get so good at writing formulas this summer.
Are we going to keep KS in millimeters?
Yeah. There's no reason to, since the diameter is also in millimeters. But, you know, we could convert both to meters, but as long as the K sub S and the diameter have the same units, then it's okay to leave them the same. Okay, so right now, there is a difference, and what that means is that we don't have the correct guess value of F. So what we're looking for is what F value makes the left-hand side and the right-hand side of the equation the same. So if we drag this down, and now of course I can actually drag it down, or I can just double-click and it will go through the bottom of the list. What we're looking for is where is the lowest difference. And so it looks like our F value is pretty close to 0.02. And we can get even closer than that by doing a goal seek. If our goal is for the difference to be 0, let's try this. Let's say data what if analysis, goal seek, and then our goal is to set the difference to a value of 0 by changing this guess of the f value, and that'll fine tune that little extra amount to find the exact perfect f value that applies in this situation. So here is our Colebrook derived f value. Now that's more precision than we need. Like if we were solving this, if we're solving some problem 0.0203, that's plenty of precision right there. All right. I know I went through this spreadsheet pretty quickly, but we've got some ground to cover today, and so if I went through it too quickly, you can refer to the recording that's posted on YouTube or posted on Blackboard, and hopefully you're going to get more familiar and more comfortable with typing these hairy equations into an Excel over time. But that is just one approach for using the Colebrook equation. You know, you could have just done these calculations on paper. If you were in the classroom with me, I'd hold up where I did this same example just kind of by hand, where, you know, in your calculator you take a guess value of f, you put it in the left-hand side of the equation, put it in the right-hand side of the equation and see if it matches, and then try a new value of f. It's pretty tedious to do it by hand. There's also a calculator way of doing it. You can solve the Colebrook equation using your calculators. Let me show you what it looks like when you solve the Colebrook equation with the calculator that I use, which is the HP50, and I'd encourage you to consider there isn't a way to solve algebraically for f. No, not with the Colebrook equation, there's not. There's a different equation called the Jain equation that isn't implicit that you could use. You know, maybe we'll come back to this YouTube video at the end of class if we end up having the time, but you can put the Colebrook equation into your Casio calculators. I think probably most people in the class are using the Casio calculator. It takes about 30 seconds for it to solve that equation, but it eventually will spit out an answer, and it'll spit out the right answer if you can keep straight assigning the variables correctly, since the Casio doesn't have all of the same variable possibilities as the letter of the alphabet. Okay, I mentioned the friction factor can also be solved with the Jain equation. And so Colebrook is valid over the entire spectrum of flow conditions. This Colebrook equation, as long as the flow conditions are greater than laminar, Colebrook will give you the right answer. So it's good. It always is true. The Jain equation is valid over a more narrow range of conditions, but it's a lot simpler, which is why we kind of like the Jain equation. It's not implicit. The Jain equation just has the f value on the left-hand side, but it's only valid from 5,000 Reynolds number up to 10 to the 8th. And then the other aspect of limitations there is the relative roughness range, from 10 to the -6 to 10 to the -2. And the truth of the matter is that that's most of the conditions that will matter to us. Most of the time when we're solving problems, we're going to get a Reynolds number within that range, and most of our relative roughnesses will be within the range. And so usually it's okay to use the Jain equation, but you should always double check the assumption to make sure that it fits within these limitations. So let me give you a chance to see what f value do you get with the Jain equation. From our previous example, we found that the f value, according to the Colebrook, is 0.0203. So I'm going to pause for a second and give you a chance to crunch the numbers on the Jain equation. Just for fun, I'll put you into the breakout groups in case you want to check answers with each other or discuss, but this will be a fast one. I'll bring you back from the breakout groups in just 4 or 5 minutes, and we'll make sure that it matches up, the Colebrook and the Jain together. Same thing with the Jain equation as it is with the Colebrook. Just note that it's okay to have units of millimeters for your K sub S and also your D because it's a ratio. So you could convert it both to meters, leave it as millimeters, but you have to be consistent in the numerator and the denominator in order to get the same value for F in the Jain equation. There is an even simpler formula than the Jain equation. As long as the Reynolds number is less than 100,000, then the Blasius equation can be determining the F value just by 0.316 divided by the Reynolds number to the 1/4 power. And so what this estimation for the F value assumes is that most likely the laminar sublayer is submerging those roughness elements that protrude into the water. If the water is moving slow, then you've got a thick laminar sublayer, and it doesn't matter so much what is the K sub S of the pipe. And so that's why this formula doesn't have K sub S as one of the variables. It just relies on the Reynolds number itself because we're assuming that the flow, although not laminar, in bulk, the average Reynolds number in the pipe isn't below 2,000, but that cushion, that laminar sublayer that can completely submerge the roughness elements, that layer is thick because of the slow moving flow. So this is another option you have available, Blasius equation, when it's below 100,000. Okay, now pipe sizing. The thing that we have to balance in hydraulic design is making sure that the pipe diameter is large enough to minimize excess head loss, but you're trying to make the pipe smaller because big pipe is expensive. Like if money was no object, and if we had no interest in optimization, then we'd make every pipe as big as we could find. You'd make every single pipe going into every home a meter in diameter, and then there'd essentially be no head losses because head losses are largely dependent on the flow velocity. But of course, that's a strange world that we won't even contemplate any further because the reality of hydraulic design is that we do care about cost, and we're always trying to find what's the smallest pipe size that's going to work for a particular situation. So sometimes you'll have a scenario where you know what head loss is going to occur through the network. And so just as an illustration, take the example that we worked in class on Monday, where we could know what the head loss through the pipe network is going to be because we know that head loss by definition would be the difference in elevation between the water surface in the tank, and if we have it filling a reservoir at the top of the building, so if maybe there was a tank on the roof that was vented to the atmosphere, and if it had no pressure head and no velocity head, and so it was just strictly the elevation head in the building, then the H sub F would be known directly. So the point is sometimes you know the expected head loss, and you know the flow rate that needs to be delivered through a certain conduit, and you maybe are getting the flow rate that's needed by an estimate of how many people are going to live in an area later on in the future, and you know how much water per person is going to be used by that population. So you synthesize some sort of an estimation of the flow rate that needs to be delivered through the pipe, and the question is what diameter and what material type is appropriate to deliver the flow that's needed. So that's the process that we're going to take a look at with this next part. We're going to go through a spreadsheet example that allows us to calculate the pipe diameter. So, why is it going to be so tricky? Remember that chicken and the egg scenario that I told you about earlier in today's lecture, that F value, the friction factor F, depends on the flow conditions. In the Blasius equation, F depends on Reynolds number, and Reynolds number depends on velocity. So F depends on velocity, and velocity depends on F. Whether you look at it through the Blasius equation or in the Jain equation, same thing. The F value depends on Reynolds number, and the Reynolds number has one of its components will be velocity, and you don't know the velocity through the pipe until you know how rough the pipe is. So that uncertainty about what is the F value that actually applies is going to make it so that we have to iteratively calculate the required pipe diameter that's needed. Okay, so we can rearrange the Darcy-Weisbach equation. The Darcy-Weisbach equation is a way of estimating energy loss due to pipe friction. So we've seen this formula several times this semester and last semester. The Darcy-Weisbach equation says your head loss due to pipe friction, H sub F, depends on the friction factor, the length of the pipe segment, the velocity of flow through the pipe segment squared, and then in the denominator the diameter of the pipe, and 2 times the gravitational acceleration. So if we have a circular pipe where the diameter is pi d squared divided by 4, then we could rearrange this equation. We can rearrange the Darcy-Weisbach equation and solve for the diameter that's required if you know what head loss is going to be experienced. And so if you know the pipe's length and you know the flow rate that will go through the pipe and you have an idea of the friction factor, then you can find the diameter that's needed. But the same thing that we had before with a chicken and the egg scenario between the friction factor and the flow velocity also exists between the friction factor and the diameter. Because if you have a big pipe diameter, then the flow velocity will be slower and your friction F value will be lower. So we're going to have iteration. F is not constant because it depends on the flow rate. Now, you may be thinking back to fluid mechanics lab last semester and remembering that the Hayes-Williams equation has just a normal C value that doesn't change with flow conditions. And that's true, but the Hayes-Williams equation isn't as accurate as the Darcy-Weisbach equation. And so, there is a model out there where your friction factor in that model won't depend on the flow conditions, but it's not going to give you appropriate accuracy for design. So that's why we're going to this trouble of struggling with the iteration that's going to be needed to get the accurate F value and the corresponding diameter. So that's just the setup. What we're going to do is go through this implicit, accurate approach of determining how big of a pipe is needed to deliver a flow rate a certain distance downstream when we know the head loss. Now, here's an outline of the process that I'm going to illustrate in the spreadsheet that we'll set up in just a moment. You have to start with a guess because you don't know what the F value is at the beginning because you don't know how big of a pipe diameter is appropriate. So we just have to cut through the red tape at the very beginning with a guess of the F value, and then with the guess you're going to find what diameter of pipe is appropriate based on that guess F value, and then you're going to calculate the Reynolds number given that diameter of pipe. Then we're going to find the relative roughness for that pipe diameter, and then we'll use the Reynolds number and the relative roughness to update the F value. So now we can replace the assumed value with a new F value that's more realistic, and it's based on the actual flow conditions. And then we'll use that new value to go through the cycle another time, and we'll keep repeating this process until there's no longer any change between the old value of F and the new updated value for F. So this is the procedure that's going to be used in the example that we'll take a look at in just a moment. Now here's the example. We know the length of the pipe, and what it is a big trunk line delivering water, and there is a lateral pipe coming off of that main trunk line, and that lateral pipe has a length of 40 meters. We know it's made out of cast iron, so we could look up the equivalent sand roughness for cast iron is 0.26 millimeters, and we need to know what diameter should be sized to ensure that it can deliver 300 liters per second. And the driving force for this flow of water is that there's going to be a head loss of 45 meters. And so where would that come from? This H sub F would come from knowing the pressure difference between the main pipeline that's providing the source of water, and then this is discharging out to the atmosphere. And so the difference in pressure is where this head loss would be determined in the example. So what we're going to do is start with an assumed value of F and calculate the diameter. Then we'll calculate with this guess diameter what's the Reynolds number in the case of S, and then we'll use the Jain equation. Since it's more direct than Colebrook, we'll use the Jain equation to get an updated F value, and then restart this process over again with the updated F value until we minimize the difference between the guess and the initial guess of the F value and the updated calculation of it. All right, so let me get my template file here, and we'll take a look at this one together. All right. So here's an outline of the process that we're going to follow. And let me see if I can share that with you over Collaborate. Let me just see if I can save this, and so that you could follow along. Maybe that would be the way to do it. That way you're not having to do this from scratch. Okay, I'm going to delete all this other stuff. Oh, I just remembered. It'll only allow me to share image, PowerPoint, and PDF files. Well, let's just see if maybe it'll let me. Pipe diameter needed. No, it won't let me share it. Let me do this then. Let me just put it on the course page, and so that you could get it there. All right. If you go to our course page, then and you can leave the Collaborate tab open and go to our course page in a separate tab, but it's this pipe diameter needed. It's an Excel file that if you have that, it'll be a pretty good starting point. You can just watch this example. You don't necessarily have to follow along, and in fact maybe just watching what I do the first time around would be worthwhile. But all right, in the problem statement, it tells us that our flow rate is 300 liters per second. Oops. Okay, so the flow rate in terms of cubic meters per second is 0.3. So 0.3 cubic meters per second. Let me zoom in a little just to make sure it's big enough. All right. The equivalent sand roughness, here I've got it set up in terms of meters because I'm going to want to have the diameter calculated in meters, so I want to be consistent in units between the two. So it's 0.26 millimeters divided by 1,000. Okay, so now that's the case of S in terms of meters. The pipe length is 40 meters in the problem statement. G is 9.81. The head loss is given as 45 meters of head loss. Okay, so I'm going to put 45 meters of head loss, and then the kinematic viscosity of water is 1e minus 6. So that will return 10 to the minus 6th. All right, start with a guess value of F. Now, I'm just pulling something out of thin air here. What if the F value is 0.015? I mean, I could start at the extreme end like we did before of 0.0008, but maybe something more in the middle of the typical values would be better because the solution will converge more quickly if you use more of a middle value. Okay, so now with the guess value of F, then we've rearranged the Darcy-Weisbach equation to solve for D. Okay, so it is 8 times L, and I'm going to anchor the reference there, times Q squared. So there's Q, anchor that reference and square it, times F. This, I'm not going to anchor the reference because I'm going to be able to copy and paste everything, and I want the reference to the F value to be relative rather than absolute. So I'm not anchoring the reference to that F. Okay. Now divided by H sub F, that is anchored. I'll put the parentheses around the denominator. Okay, times G times pi squared and close parentheses around everything, and then it's to the 1/5 power, so to the power of 1 divided by 5. Okay, so what this is saying is it's telling me what diameter of pipe is needed to accommodate the flow for a certain head loss, for a certain pipe length, for a certain flow rate, if I have this guess F value being the F value that applies. So it tells me that the pipe would need to be 0.158 meters in diameter under these conditions. Okay, so now if that actually is the pipe diameter, then the flow rate is going to be the same as it was before. But now let's calculate the area that applies for that particular diameter. So area is pi d squared divided by 4. Okay, so that gives me the cross-sectional area, and then the velocity is Q divided by the area. So the water is going to be moving at a velocity of 15.25 meters per second through that pipe. And now the Reynolds number I can calculate with our Reynolds number formula. So we're talking about the Reynolds number with this particular flow conditions. So with this velocity, with this diameter, and then our usual standard kinematic viscosity. That hasn't changed, so I'm going to anchor the reference up to that so it always looks in the correct spot for the kinematic viscosity. So that would be the Reynolds number if this is the diameter. And now I'm going to get my updated F value. So I'll calculate an updated F value using the Jain equation. So my new F value is 1.325 divided by the logarithm of K sub S, anchor that reference, divided by 3.7 times D, and the D that I'm talking about is the D that we've just calculated. Okay. And then plus the right-hand side 5.74 divided by the Reynolds number, here is the Reynolds number, to the power of 0.9. It's so easy to write the wrong thing. Let's see, how many parentheses? That one closes it out. All right, and then squared. So we have an updated F value, 0.0224. And so My guess F value was 0.015 and my new value is 0.224. Let's, just to get an idea of whether this is converging, let's calculate the percent difference. So the percent difference would be the new value, well, let me first put a parentheses, the new value minus the old value, and then divide by the new value times 100. 33%. So that's not so good. We haven't converged yet. We want it to be closer, the input and the output F value to be closer. That will be the indication that our solution is converged. So now, in the second iteration, things are going to be easier because we're just going to be able to copy and paste a lot of the formulas that have been typed in before. We won't have to type it from scratch the second time like we did the first time. So the F value, I'm going to use this new updated F value. Okay, now what about the diameter? Well, let me just copy this formula rather than typing it again. I'm just going to highlight that and I'm going to press Control C, and then down here I'll press Control V, and it's calculated the diameter. Let me click in here. All of the references up to the constants remain, referring to the constants, but the reference to this F value is looking now at our new iterated F value. So here's our updated guess of the diameter, and then for these flow conditions I can just copy, Control C, and paste, Control V, and well, it looks like maybe I need to reference the correct flow rate. Did I not anchor that reference? Looks like no, I didn't. So I should have anchored that reference so I could copy it again. So let me copy and paste again. So Control C, Control V. All right, so now I have an updated area and velocity that will occur if this is the diameter. Okay, and now this is the updated Reynolds number, and now the new F value and the percent difference. I can copy that and paste it. Things are converging. We had a 33% change in our first iteration, and now in the second iteration, the input and the output F value only changed by 2%. So we'll do one more iteration just to make sure that we've got it all, but we can do the whole thing. Let's see, assume an F value. Let me just copy all of this. See if I can do it all at once. So Control C, and no. I've got too many spaces. I'm going to have to just do this. So the F value is the output of our last one. Assume, okay, so it's going to be that. And everything else I think I can copy all at once. Okay, and I'll need to paste it in the right location. I'm going to start here and paste it. So we've got our updated diameter. Here's our new velocity and Reynolds number. And then the last part will be the F values. And it has converged. The input guess value that we had for the F was 0.0219. The output is essentially the same, 0.0219, less than 1% difference. And so now we say this is the diameter that's needed. So this is our answer. The answer to the example, this is the pipe diameter that should be used for the design. 0.170. Now, they probably don't make a pipe exactly that diameter. So what you'd need to do is you'd need to buy the next larger commercial available pipe size. So you'd round up, and then it would turn out that your head loss would be slightly less than the 45 meters of head loss that was anticipated. All right, well, I regret that we had to kind of speed through that example, and I also apologize that I didn't send you this template file earlier. If I would have thought about that, I think it maybe would have made things a little bit easier. So I apologize, and I'll try and remember in the future if I'm going to use a spreadsheet template like this, I'll try and get that to you before the lecture begins. You know, with Excel, there's just a million different ways you can put in one too many parentheses or click on the wrong cell, and things can get messed up so easy. It's a powerful tool, but sometimes your mistake is hard to find, and that's one of the reasons I'm sorry that we're not in the same classroom together, is it would be much easier for me to help you find your mistake if you had an error as we were going through it if we were together in person. But you know, go through it. You can refer to the video if you need to take a second look at what we did, and of course you can call me on Teams and share your screen with me, and I'd be happy to take a look at what you've got if you need some practice. That's our method for finding D. When we get together on Friday, we're going to take a look at a non-iterative approach that's required that's available for solving diameter. Dalton asks, when you're doing homework, do you recommend using paper or an Excel sheet? I would recommend using Excel for finding the required pipe diameter. You can do it on paper if you like, but just the iteration, you know, like how I did that copy-paste thing, it's much easier to just do copy-paste than to redo the calculations by hand. But if you're more comfortable doing it by hand, that's okay. Okay, well, that's it for today. Hope everybody has a good one, and I will see you on Friday.